are on page 759 today, and what I would like you to do is we're going to take what we did yesterday with Helen and her compounding interest. And remember, yesterday with Helen, we found that she had an A of t equaling p times 1 plus r divided by n to the nt power. We developed that formula yesterday, okay? And that was when we compounded it a certain amount of times over years. Okay? So today, Helen found a new bank. Okay? She found a bank that offers her 100% interest. Okay? And the reason that this bank is offering her 100% interest is it's easier for us to develop what we need to develop with 100% interest. Okay? So she goes to the bank and she deposits $1 in the bank. Okay? So $1 at 100% interest, and the bank says, well, what do you want us to compound it at? They're that flexible. Okay? So she says, well, yearly. They go, okay. So Helen's smart because she was in class yesterday. She says, all right, so I'm going to put $1. I'm going to put $1 into my formula. So 1 there. 1 is 1 from the formula. My interest rate is 100%, so that in decimal form is 1. And if we're only compounding it once a year, then we get that. And so do all that math. She's got $2 in her bank account every year. But she says, well, wait. Yesterday we learned that the more times we compound it, the better off we are. Right? Okay. So she says, what if we do it every 6 months at this new bank? And they do the calculations and they say, well, you'd have $2.25 in your bank account at the end of the year. Okay? Better. Okay? Your job now is to fill in the rest of the chart. Okay? Go for it. So quarterly, we should have gotten 2.44141. Monthly, 1 times 1 over 12, 12 times 1 power. We should have gotten 2.61304. Weekly, how many weeks in a year? 52 weeks in a year. So then that goes to 1 and 1 plus 1 over 52 to the 52nd power. And I get 2.69260. Daily, how many days? 365. And I get 2.71457. Yeah. How many hours in a year? Okay, and then there I got 2.71813. How many minutes in a year? And there I got 2.71828. How many seconds in a year? And there I got 2.71828. question number 2. Question number 2 is make an observation about the frequency of compounding and the amount that Helen earns. Okay? So look at the chart, talk about what the chart actually means and how that relates then to question number 2. All right, so since we're talking about worksheets already in some groups, okay, what does this chart, before we get to question number 2, what does this chart actually show? What does it show? You got Max? So it shows like how many times you're compounding on the same conditions, right? Okay, and that the more and the more and the more and the more times that you compound it, it really doesn't change it anymore. But whereas like from way up above, let me scroll up just a little bit here. Whereas from like yearly to every second, there's a pretty significant difference. Okay, all right, I agree with that. Okay, what? Okay, so spitballing here, okay, going off the cuff, if you will, if we compounded, if I was the banker and you were Helen, and I compounded your money every half of a second, what do you think the blue number would be? Probably be the same thing, and then the decimal places out here a little farther would probably be a little bit different, but really when we're talking money, okay, we're really only looking at, really you're looking at the first 3, okay, because then that third one is the one that you round to the penny. Okay, all right, so the frequency of compounding and the amount that Helen earns, it's approaching, the more times you compound, it's approaching $2.71 2.71828 cents, right? Okay, so it's getting closer and closer and closer to that number. Okay, turn El Pajo. That number is a special number in math. It's an irrational number, and it's called E. Now, E, you're going to want to think about E as a variable because it's a letter. Okay? But I'm telling you right now, from this day forward, E is no longer a variable. E is Euler's number. Okay? It's Euler's constant. We'll talk about Euler down here when we get to the 4th paragraph. Okay? It's the natural base. Okay? In geometry, what it's similar to, in geometry you work with pi. Okay? And instead of writing out 3.14159265, so on and so on and so forth, okay, we just write pi because it's shorter to just write pi than writing out all those numbers. Okay? So that's kind of what E is. Instead of writing out 2.71828182845945, so on and so on and so on, okay? And if my name was Bakhar Karmakar, I would go out 5,002 places with it. Okay? So that's what the little thought bubble did. He memorized E out to 5,002 places. Okay? Okay? I don't know how you do that because that's a full-time job right there. Okay? So E is used to represent the constant that we found from Helen's things. It's often used in such things as population models. That's big in population models. We'll get to that in a minute. As well as radioactive decay. Okay? And it's vital in physics and calculus. Okay? All right? I'm trying to think. Okay? make a side note down here. Okay? This paragraph, I'm going to skip the talking about Euler and we'll come back to it. E is used in continuous growth. Okay? E represents continuous growth. So if you see in a problem the word continuous, you're automatically going to be thinking Euler's number E. Okay? Now, half-life. We did a problem, a while back that dealt with half-life, right? Okay? What is half-life? What's the concept of half-life again? After a certain amount of time, okay, let's say 5 years, how much do we have left? Half of it, right? Okay, so we're basically dividing by 2, right? Now, let's say that this piece of paper has a half-life of 1 minute. Okay, so it would decay. So every minute, it's going to be half left, right? Okay, here we go. So the paper, we'll start it, okay? And luckily for you guys, I have a fast forward button on time, okay? So here's our piece of paper, right? Okay, and then 1 minute later, all of a sudden, magically, there's only half of it left, right? Okay, is that how decay works? That right at that half-life time, boom, half of it's gone. So it slowly goes away over time. So as we're starting here, so then like a little bit goes, right? And then a little bit more goes, right? And then a little bit more goes. Okay? And then once a minute's gone, then bam, there's only a half left. But then it keeps going, right? And so then a little bit more goes and a little bit more goes, so that, right? The change is continuous. It's not we wait, then after a minute, boom, half of it's gone. Then in the next minute, half of that's gone. Okay? It's a continuous process. Okay? That's where E is going to come in. Okay? E was found by Leonhard Euler. Now you may say to yourself, well, that's Euler, okay? But it's actually pronounced Euler. Okay? And he did this all when he was 21. Okay? He found it when he was 21. He basically came up with the compound interest thing and kept going. He did that chart that we just did, and he realized, oh, this is going out to pretty far. Now, if you'll notice, 1727, okay, do you think he had a solar-powered Texas Instruments calculator on his desk? No deal. He did all that calculations by hand.
Wait, so is E like that number?
E is this number right here. Yep, this 2.71. Yep, that's what E is. And if on your calculators, usually it's the inverse of one of the log keys. Okay? If you went E to the first on your calculator, you would get 2.71. 82818, I think you'd get to. I think you get to the 1.8. You might get to 2 then at the end. Okay? It's not Bueller, Euler. Yep. Okay? Alright. So let's put this to work here on page 761. Okay? So on page 761, we have the formula for population growth. Now, this is the formula that the book gives you, but I hate to break it to you, there's an even easier one that's the same style of it. Okay? Instead, we go with A equals PERT. Okay? Okay? PERT. Okay? So that your n sub 0 here is really P. Okay? And your n of t is really A. Okay? It's the same formula, it's just easier to remember because it's my shampoo.
Is it P? Is it
And n sub 0 is P.
So it's
E is E.
Oh, that's right.
It's the same one as this.
Yeah. It's E.
Yes.
Yeah, E is E. It's not a variable anymore. It's E. Okay? So, what this means is, so P or n sub 0, that's going to be your starting amount. Okay? However many things you have. If it's population, it's how many people you have. If it's a radioactive decay problem, it's how many grams or pounds or milligrams or however much amount you have of your substance. Okay, pieces of paper, so on and so forth. Okay? R is going to be your rate of change. Now, here's the cool thing about exponential functions with E. Okay? When we were doing growth and decay functions yesterday and the day before, and when we were doing them then, okay, we had to have B values in certain ranges, right? If it was a growth function, B value had to be above 1. If it was a decay function, B value had to be between 0 and 1. Okay? Here's the cool thing about E. The nice thing is, if R is positive, your function is going to grow. Okay? Because if you think about it this way, let's make a graph here. E to the x power, that's a growth, right? Think about it in terms of our a times b to the x, right? What's b in this case? B is e, right? Well, and what value is e? 2 point something, right? Which, when we're thinking about exponential growth functions, 2.71828 is bigger than 1. So that's a growth function, right? Okay. So if my exponent is positive, it's going to grow. Okay. What about if we want it to decay? We have to have a negative R value. Okay. So if I go back to my graph here now, and I put on here, okay, good, it didn't do it, e to the negative x, that's going to be a decay. Because now, that's really 1 over 2.71, which is between 0 and 1. Okay. T, here's another cool thing about PERT. T is time. In that compound interest one that we did yesterday, or that compounding one, T was years, and it's always years. In PERT, it's whatever you have. If it's 1 minute for a decay of a piece of paper, okay, then that's what your time is. Your time is in minutes. If it's years, it's years. Okay? It doesn't matter what time frame you are. It's whatever your problem is based off of. Okay? And then this last one is your outcome, what you're looking for. Okay? So, if this were a population problem, why do we use E as the base in a population problem? Talk to me.
Maybe because it stays the same.
It does not stay the same all the time. Because E represents continuous growth, right? Okay? And so, as far as I know, and granted, I've only had 2 kids, okay? But as far as I know, I was not mandated that they had to be born on the 13th of every month, or of the month that they were born. You know what I mean? It's not like it goes back to this paper problem. It's not like all of a sudden every baby needs to be born at this certain day. You know what I mean? It's a continuously changing thing. Okay? 1 second, baby got born over at Aspirus. Okay? Oops, there was an old person at one of the nursing homes just passed on. Oops, next second, twins got born at the Weston Hospital. Okay? Oop, there was a bad accident. 3 people died tragically in a car accident. Okay? It's changing. It's continuously changing, population is. And because of the word continuous then, that's why we use E. Okay? Sometimes it's good change, sometimes it's bad change. Okay? How would this formula be used to represent a decline in population? What would we change in our formula to make it be a decline in population or a decay of population? We'd have to have a negative exponent, so R would be negative. Because T wouldn't be negative because we're not looking back in time. Okay? But we can make T be negative to go back in time. Okay? But R would be negative there. Okay? So in a problem, if it says like 4.8% growth, that's a positive 0.048 as your R value. Okay? If it says it declined by 5.7%, your R value is negative 0.057. Okay? So you gotta read the problem in order to find those. On page 762, I would like you to do question 4, A, B, and C, and then we'll do question 5 together. Spot check here, just a quick spot check. Okay, so because we see this word right here, that means we think what, Scott? E. We think E. Okay, so we're thinking A equals. Oops, I almost wrote out the whole word PERT. I gotta do the E. Come on now, better than that. Okay, so we're thinking PERT. Okay, so the amount that we have, or the amount of people living in Fredericksburg, is equal to, what did we start with? 19,360 times E to the 0.029 or 0.029 T power. That's our formula. Okay? Use that now then to do B and C. So, if I'm going to use that blue function, what do I need? I need T, right? Okay? So in 2013, what is my T? My T is 13. Because we started in the year 2000. So that's 13 years from there. So my function then would be A equals 19,360 times E When I type that into a calculator, I get 28,225.027429,426 people.
You want us to do decimals then? You can't have decimals.
Claire says we can't have decimals for people.
Yeah.
Okay? So what would an answer be here? 28,225 people.
Yeah.
Okay. Can't have part of a person. Okay. If you, Jacob, I'd go either way. I'd go 2-6 there too if you want. You know what I mean?
That's how I was.
Yeah. Okay. Yeah. If you round it up because that, because you got a part of one, that's fine. Okay. In C, what is the year 1980 in terms of T? -20. So my A equals 19,360 times E to the 0.029 times -20 is going to be 10,839.632376,706 people. What do you want to round that one to? 10,840 people. Okay. Yes?
Yep.
Okay. Fantastic. Question number 5 says, let's use a graphing calculator. Here is a graphing calculator. Actually, I'm going to go a whole new one because I want to get blue. Okay. And we are going to use there it is. I couldn't find my page. Use the graphing calculator to estimate the number of years it would take Fredericksburg to grow to 40,000 people, assuming that the population trend continues. So I should probably put in here my function, right? So my function started with that, and then I went e to the 0.029 t power, right? But instead of putting t on the graphing calculator, I have to put x. Okay. And there is my...
Adjust the window settings.
Oh, let's adjust the window settings. Okay. What do we want to adjust the window settings to? Well, X is first.
Probably like 50 something.
So the X min is 50 something?
It only needs to be between 0 and 1. No, we'll put 0 to 9. We're already at like 13.
So tell me what my X min should be.
Well, yeah,
Negative 10 is fine? Do we agree with negative 10 being fine? Last class chose 2013 as their X min.
because that's a year.
I'm just telling you what they chose.
No. That doesn't seem right. Like 2015?
They literally put in there, they went 2013. That's what they did, because in the year 2013, it was 28,225 people, and that's less than 40,000. Do you want to do that also? I got a couple of head shakes yes, and a couple of head shakes no. Let's try it and see, okay? So then, what do we need to put as our maximum? 2050? Okay. I'm going to go by 5 years, 5-year stretches there. Okay. Y's then.
40,000 or 10,000.
10,000. 50,000. Let's go by 5,000. Oops. Too many. So there's my function. Not my function groups. What's wrong with it? I should see it, right? What's wrong? What years are we actually searching here? No. No, what years are we searching?
Well, you should be searching like
On this graph, what years are we searching?
probably like 15 to 30.
No. We're searching the year 4013 to the year 4050. Think about it back here. What did you put in as your t-values?
How many years passed?
Past 2000 is what we put in for our t-values. Okay? So we got to go back here now, and we've got to readjust our windows. Okay? So I'm going to go back to -10. I liked that one. What do we want to go out to? 50? 30? 30? Let's cut it in half. We'll go 40. Okay? We'll still go by 5s. Y-min? That's fine. Okay? No offense, I'm going to go -2500. I like to see my axes. I'm crazy like that. Oops, I went 50,000 there. I only want to go 5,000. Okay? So there it is. Alright? I like it. Okay? So where is it equal to 40,000? How do you know that?
Just put it in on the
Because what?
Just put it in on the intercept.
What do you mean on the intercept thing?
Isn't there a way that you can?
There is a way.
You can put in 40,000 and then.
So put in 40,000?
Yeah, and then it'll just put.
Whoa, tap the brake. Now it's doing it. Now it's getting all funky. That's 4D.
Yeah, there you go.
Okay? And then what? Now we do the intersection. Okay? So what does that mean? No. In what? In the year 2025, the population will be 40,000 people. Okay? Because remember that X value was years after 2000. Okay? Good times. Tomorrow, you will have a formative assessment in class. Okay? And I want to say it was it green or was it yellow yesterday? It was yellow yesterday? Okay. The yellow homework sheet will be due on Friday. Okay.
Yeah.
So yeah, so we have green and yellow. Yeah, so green and yellow due Friday. No, is it green? It should be blue. Blue, yeah, because we always go blue, yellow. Blue, yellow, green, purple is the order. I don't know if you've noticed that. We've ordered the colors the same in every unit so far. Okay? So blue and yellow due on Friday. Okay? Formative assessment tomorrow.